All right, hello and welcome to our second lecture in Chem 390, Chemistry of Wildfires, where the topic of today's lecture is going to be all about the stratosphere. If you don't know what the stratosphere is, that's okay. I'm going to define it. And specifically, we're going to be talking about stratospheric ozone. So this molecule is 3 oxygen atoms linked together. The oxygen we're used to breathing, and that makes up about 20% of our atmosphere, is O2. O3 is very, very, very different in terms of its chemistry, as we'll learn in this lecture. Okay? And this is a very recent topic of interest in the realm of atmospheric chemistry related to wildfires. As you can see here, I have 2 of the resources I used in preparing this lecture, where these are just the titles of the journal articles that I used, and they are very recent, so both from 2022. And if you don't know anything about publishing research in science, there are good journals to publish in where the research results are very groundbreaking and very exciting. Those really, really good journals include things like Science. So the journal Science is a very, very difficult journal to get published in because your work needs to be extremely thorough as well as extremely groundbreaking and innovative. And then also the Proceedings of the National Academy of Sciences, or PNAS, is another really, really, really big journal. And I'm not showing a third preprint journal article that I used for this lecture, but that one was it wasn't published in Nature, but the publisher Nature manages also like preprints, which are not peer reviewed, but still is for a place for exciting new research that you just want to get out the door and get people knowledgeable about it. It goes through that avenue. All I'm trying to say here is that a lot of really, really big journals are publishing some really interesting and really troubling science on the effects wildfire smoke have on stratospheric ozone. Okay, so just to give you a quick overview for the lecture today. First, we're going to talk about the Earth's atmosphere. I don't expect you to have a thorough understanding of the different regions of the atmosphere, what they do, what chemical processes occur in those. So we need to lay the foundation in that sense. So I'm going to go over all of that. And then we'll talk about stratospheric ozone destruction. We'll talk about a little bit of brief history, which will give us an understanding, or rather give you an understanding of how ozone can be depleted in the stratosphere and why it's bad. And then we'll touch on how do wildfires specifically destroy stratospheric ozone, okay? And just to tie this into our last lecture, because it will build off of that, just remember that last time we talked about particulate matter mostly, which is one of the main components given off from wildfire smoke. So we talked about particulate matter, and we identified a series of categories that are going to be relevant in our subsequent lectures in Chem 390. So we had elemental carbon, EC. We had organic carbon, which will be a big one today. We had chlorine, not chloride. There's no negative here. This is just a neutral chlorine atom. That will also be a big topic for today. And then we also had nitrates, and some trace elements that we'll get to in wildfire ash. But just remember, wildfires give off particulate matter, and that will be a big topic for today to explain how wildfire smoke can destroy stratospheric ozone. Okay, so let's just jump straight into the atmosphere. So the Earth's atmosphere can be broken into regions. All right, so I have on this slide the Earth. And then let's say we were to zoom in on the surface here and measure altitude away from the Earth's surface in kilometers. I'll give mile comparisons as well, just because maybe it's easier for you to think of things in terms of miles, whatever. But anyway, so the Earth's atmosphere as you might imagine, is composed of a lot of gases, a lot of particulate matter in it. And we like to, or rather atmospheric physicists and chemists and scientists like to think of the atmosphere in discrete regions, okay? So the first discrete region is from Earth's surface, or 0 kilometers away, all the way up to about 12 kilometers. This region here is called the troposphere. I realize I didn't give myself a lot of room to write this, but hopefully it'll be fine. And let me just double check right now that my screen is not blocking any of this, because I think it will be. Okay, we're back. Hopefully I fixed it. It's hard to tell, but I think we're going to be okay. But anyway, we have the troposphere in the region of 0 to 12 kilometers above the Earth's surface. And in this region, it's interesting to note that 85% of the air mass in the atmosphere resides in the troposphere. So 0 to 12 kilometers, almost all matter that exists in the air is going to be present in this region, okay? And then beyond that, from 12 to, I believe, 48 kilometers, so a much bigger region here. I'll use a different color for the stratosphere. But I guess I stole my thunder there. This region, from 12 to 48 kilometers, this is called the stratosphere. And the stratosphere, running out of room, has about 15% of the air mass in it. Okay, so of all the stuff in the air that is in the Earth's atmosphere, just 15% of it resides in the stratosphere. And then we could keep going. There's more layers. And, you know, I realize 85 plus 15 adds up to 100. So you might think, well, is there just nothing above the stratosphere? No, there is. There's just such a small amount that it would be less than 1%. And these are rounded figures anyway. Don't fixate too much on that. The important part is that the first two layers of the atmosphere can be broken down into the troposphere and the stratosphere. And then above that, there are subsequent layers that we don't need to worry about just because the chemical processes that occur up there are not very important for today's lecture, okay? Just take my word for it. And you might be wondering, well, this seems like an arbitrary cutoff. Why 12 to 48? What's up with that? And the reason for it is because there's a very interesting physical phenomenon that results because of the chemical processes that occur in the stratosphere. And that physical phenomenon that I'm alluding to here is the fact that the temperature, the average temperature of the stratosphere is actually higher than the average temperature of the troposphere, which you would not expect to be the case. You would expect as you get farther away from Earth, it gets colder. And if we were to look at a plot of temperature versus altitude here, if we started at 0 being at the Earth's surface, the temperature would be like room temp. So in Celsius, that's like 20 degrees Celsius or so, or like, what would that be? Like 75-ish, I think. Yeah, like 72, something like that. Just like, and it obviously is going to depend on where you are on Earth and what season it is, but average temperature at the Earth's surface might be something like 20 degrees Celsius, and as you move up away from the Earth's surface, what happens is temperature starts to drop, and then right when you hit this 12-kilometer mark, I never gave my mile comparisons here, I'll do that in a sec, but once you hit this 12-kilometer point, the temperature actually stops dropping and it actually increases and forms a peak like so, and then it decreases again. And this region of where the temperature is inverted from what you would think based on simple physics, that is what defines the stratosphere. And the prefix stratos comes from Latin, I believe, and it means to mix things or to separate into layers. So that is why it is called the stratosphere, because it is a distinct layer in the atmosphere where temperature is inverted. And because hot air rises and cold air sinks, these do not mix. The stratosphere and the troposphere do not mix very readily with each other. Just because the warm air wants to stay up high in the stratosphere, the relatively colder air in the troposphere wants to stay low. So as a result, really no mixing occurs and this layer persists. Okay? Okay, so now for the mile comparisons. I guess it's really not that important. But 12 kilometers is about 7.5 miles. And then 48 kilometers is about 30 miles. So in the region from 7.5 miles to 30 miles above the Earth's surface, that is the stratosphere. And I realize also I got my bounds wrong on this graph. The edge of the stratosphere, so clearly this graph is not to scale, but that's okay. The edge of the stratosphere, the upper boundary, is marked by the region where temperature starts to decrease again as you go up in altitude, okay? So this odd region of where temperature increases as you get farther away from the Earth, that is what marks the stratosphere, okay? So that's our stratosphere. And as we'll see in a second, the chemistry that causes this temperature inversion is really interesting and is related to ozone production. So let's just jump right into it. So a good place to start before we get into any chemistry is what chemicals are up there in the Earth's atmosphere. Well, so if we were to consider Earth's atmospheric composition, there's really, there's a lot of things, but there's really only three that we need to talk about to basically get to 100%. And beyond that, everything makes up less than 1%. So we have about 78%, 78% of the Earth's atmosphere composition is nitrogen. So it's an inert gas, doesn't really do anything. You're breathing it in right now as you speak, and you're breathing it right back out because your body doesn't really do anything to it, and it doesn't really react with your body a whole bunch. This is very important for nitrogen, the nitrogen cycle, and natural nitrogen source to be in soil. We'll talk about that a little bit later in the course. But for now, just know that a lot of the Earth's atmosphere is stuff that doesn't do a whole bunch, to be honest. And then about 21% is oxygen gas. This is very important. We need that to breathe or to live. So what we do when we breathe in oxygen. It binds to hemoglobin in our blood. Our heart pumps that blood to all of our muscles, so we get oxygen to our muscles so we can function and survive. And then if we do some math here, this puts us at about 99%. 78 plus 21 is about 99. So the last about 1%, and remember, there's not just three things in the atmosphere, it's just that beyond these three that I'm listing here, things make up less than 1% of our atmosphere. So it might have to add up to 100, but in reality, it's adding up to like 99.9. And then the rest fill up that last 0.1%. Okay? So the last 1%, surprisingly, you might not have guessed this, is argon. Argon gas. It's a noble gas, so dubbed because it doesn't really react with anything. And interestingly enough, the argon in the atmosphere comes from the fact that a small fraction of potassium atoms, so think like a banana, there's a lot of potassium in there. Potatoes have a lot of potassium as well. I can't remember the exact number, but a certain fraction of potassium atoms are radioactive, and as they decay, through radioactive decay, they are converted into argon. which is a gas. So a lot of the argon in the atmosphere comes from potassium radioactive decay. A little fun fact for you. Where am I going with this? Okay, but anyway, the important stuff for the atmospheric chemistry that we're going to be talking about, at least on this slide, is pretty much all entirely O2. That's where ozone comes from or that's how it is formed in the stratosphere. So let's think about how that happens, okay? So I have here a little picture of the Earth's surface. So we're just focused on a surface of water, I guess, whatever. Doesn't really matter what the surface is, land or water. We're caring about what's in the sky here, what's in the atmosphere. And then I have this dotted line to represent the boundary between the troposphere and the stratosphere, okay? So what's really important in atmospheric chemistry is the fact that sunlight is very, very abundant, okay? By the time it reaches us here on Earth, a lot of the sunlight is either reflected back into space from clouds, or it could be absorbed by molecules in the air. But one thing that is in abundance in the upper regions of the stratosphere is light. There's lots and lots of light. So a lot of the reactions that occur in this upper region of the stratosphere is what we call photochemistry. Photochemistry meaning chemical transformations that are carried about through the absorption of light, photons. So the sun, as you might be well aware of, emits light. So I'll just draw some light rays. And we don't really have time to talk about really the wave nature of light, but basically just know that we can separate the light emitted by the sun into characteristic wavelengths, okay? So the sun emits just broadband light, meaning light with a wide range of wavelengths, and these wavelengths include UV light. So there's UV light and visible light, which is what we are using right now. That's what the cone receptors in our eyes are detecting to allow us to see. We're detecting visible light. And technically it also emits, really the sun emits gamma rays all the way to radio waves, but for our discussion here, it's really the UV that's going to be important, the important driver for the photochemical reactions that occur in the stratosphere, okay? So let's just zoom in on UV light specifically. UV can be broken into three major categories. There's UVC, UVA, or UVB, and UVA. You might have heard of these if you look at like sunscreen bottles. It'll say like protects against UVB and UVA, stuff like that. What that's referring to is let's just say the type of UV light, okay? So UVC light is the most harmful, let's say, to biological life, but that's not the right terminology here. Really what it is it has the most energy in a photon of UVC light, whereas UVA, at least in terms of UV, has the least amount of energy. So if you were to pick which you wanted to be exposed to, would you rather be exposed to UVC or UVA? Well, UVA can actually be good for you because, that's what allows us to make vitamin D in our bodies is from absorbing ultraviolet light. But UVC, that's no good. You don't want to be exposed to that a whole bunch. That's what causes really harmful, or it can cause really harmful health effects. Luckily, we have oxygen in the atmosphere that can remove UVC so that we are basically never exposed to it, okay? So in this upper region of the stratosphere, I'll put my little boundary mark in here. In this upper region of the stratosphere, the first thing that happens photochemically is molecules of O2 that are up there will absorb UVC light and split to form into two oxygen atoms, just atoms that aren't bound, okay? And what they'll do then, these two oxygen atoms can bump into each other again, reform the oxygen, which will then absorb more UVC, split apart to oxygen atoms. As they're moving around in the atmosphere, they can bump into each other, form O2 again, which can absorb UVC light and split apart, and it's just a cycle that goes over and over and over again. And it removes UVC light, so by the time the light reaches Earth's surface, we are not exposed to that. So O2 is really good for that purpose. It's also good for the fact that we need it to live, but also good in the stratosphere. You would think, 48 kilometers up in the sky, who cares? Why is that relevant at all? And I should also mention, if I'm being a completionist here, that this process of photochemical O2 splitting with UVC light occurs well above the stratosphere as well, because there's oxygen up there too. So above the stratosphere and the mesosphere and the exosphere, this process is happening, and it is also happening in the very upper region of the stratosphere, okay? So it is not just the stratosphere where UVC light is being absorbed, okay? But this is step one, okay? So by the time the light from the sun reaches now like mid-latitude regions, what happens is the O2 molecules in the upper regions of the atmosphere, as they split apart and form two oxygen atoms, the most probable thing for these two oxygen atoms to do is just bump into another oxygen atom and form O2 again, okay? But as we get down to these lower regions of the atmosphere, there is less UVC light. So what that means is that as this process occurs, it will still occur to a much lesser extent. But now, in this lower region of the stratosphere, the most probable thing for these oxygen atoms to do is not bump into another oxygen atom, just because there's not a lot of UVC light, there's not a lot of O2 being split to form oxygen atoms. Rather, what happens is, I'll put this in a different color, those free oxygen atoms, it is more probable for them to bump into another oxygen atom, or sorry, oxygen molecule that has not absorbed UVC light, okay? And what this does is it forms ozone, O3, and this is what we call an exothermic reaction, or it releases heat. Hence, the temperature inversion we see in the stratosphere. This is from ozone formation. So just to reiterate, just because it can be, there's a lot of information here. So what happens here is that light from the sun enters the atmosphere. Where light is most intense, or in the upper regions of the atmosphere, O2 gets split into oxygen atoms, and because UVC light is so abundant in the upper regions of the atmosphere, pretty much any O2 molecule will absorb UVC light and break apart to oxygen atoms. There is no, all of it gets completely depleted, and then those oxygen atoms bump into each other to reform the O2, okay? But as you get further down into the atmosphere, most of the UVC light has already been absorbed by oxygen molecules. There's still a little bit there, so this oxygen can still absorb some UVC light to split apart. And now in doing so, you have oxygen atoms and also a lot of unreacted oxygen molecules, O2. So now what happens is those free oxygen atoms don't bump into another oxygen atom. Certainly they can. It's just in terms of probability, less likely to do so. It's more likely to bump into a free oxygen molecule that is very abundant in this lower region of the atmosphere. And in doing so, it forms ozone, and this ozone produces heat, creating that temperature inversion, which is what leads to the classification of the stratosphere. So the stratosphere is where this sort of Goldilocks zone exists, where there's enough UVC light to split some of the oxygen to oxygen molecules into oxygen atoms, and there's enough unreacted oxygen molecules so that the resulting oxygen atoms from photochemical oxygen photolysis is the word that I want to say, but splitting apart from light. So the oxygen atoms that result from that bump into an oxygen molecule and form ozone, okay? And I should also mention, you might be screaming at the computer screen right now, what about nitrogen? Why doesn't nitrogen take part in all of this? Well, if an oxygen atom bumps into a nitrogen, nothing happens. They don't form a molecule. Well, they don't usually form a molecule, okay? The most probable thing for this oxygen atom to do in the lower parts of the atmosphere is to bump into an oxygen molecule, form ozone. Okay, so all right, I'll stop rambling. And what's important about ozone is that ozone is able to absorb UVB light. So this cannot be absorbed by O2, or at least not a whole bunch. And this will split into O2 plus an oxygen atom again. So this is the real benefit of this photochemical process in the stratosphere. Ozone is very important in the stratosphere because it removes UV light, or rather it absorbs UVB light so that less of it reaches Earth's surface. Where UVB light is still fairly harmful, where it can cause cataracts and skin cancer and harm biological life, ozone helps to remove that UVB light so that when we put on sunscreen, what we're really worrying about is mostly UVA and a little bit of UVB that might squeak through the ozone, okay? And this process is very, very, very important for life to exist, because if we were constantly bombarded with UVB light, say there was no ozone in the stratosphere, we would certainly not exist the way we do today, just because UVB light can still be very harmful to humans and other biological life. All right, and then just to complete our picture here, the last thing that happens is light makes its way to Earth, and this light is mostly comprised of UVA light and visible light. Okay, so the purpose, the real benefit of these upper regions of the atmosphere, so like the stratosphere and even above that, even though there's only 15% of the total air mass resides in the stratosphere, it is incredibly important for ensuring that UVC and UVB light do not reach Earth's surface. So let's just try to make this a little bit more orderly here. So what are the order of operations here? So step 1, O2 absorbs UVC. Okay, and then step 2, O atoms that results from O2, I'll use the word photolysis here. So lysis means to split. So when I say photolysis, I'm saying the splitting of O2 by UVC light. So the O atoms that result from this bump into or react O2 molecules that have not reacted, and then this forms ozone. and heat, which is important because that's what causes the temperature inversion of the stratosphere and prevents it from mixing with the troposphere to a large extent. Okay? And then step 3, why is ozone important? Ozone absorbs UVB, which is good. And then I also should mention that ozone can be regenerated from just more oxygen molecules and oxygen atoms bumping into each other. So ozone has a natural cycle where it is depleted by absorbing UVB light and then reformed from oxygen atoms and oxygen molecules bumping into each other. Okay. Right, so hopefully this is sort of making sense what's happening in the stratosphere. So this is all in the stratosphere, by the way, and above, technically. The UVC light being absorbed by O2 can happen above the stratosphere. And I'm sort of trying to set the stage here. Hopefully I'm succeeding because I'm going to then talk about pivot to, well, how can ozone be destroyed and how can wildfires contribute to that destruction? Okay, so let's jump right into that. Let's talk about ozone destruction, and we'll talk about specifically the history of ozone destruction, which is another really interesting field of science and really represents one of the greatest concerted efforts by mankind to address a scientific issue that was caused by man and correct it. Okay? So our discussion of ozone destruction, and I really should say anthropogenic. I'm really second guessing this spelling right now, but I think that's right. Maybe it's an A, anthropogenic? You get the idea. Man-made, man-caused. I'm really referring to man-caused ozone destruction, because as we saw before, ozone getting destroyed, I just said, was a good thing. It's good when ozone gets depleted or destroyed by absorbing UVB light because there's a natural cycle here. It will absorb UVB, it will reform, and so on and so forth. That's good. So what I'm talking about here with the history of ozone destruction and the ozone hole is specifically how did anthropogenic reasons lead to the destruction of ozone. And our journey into this history starts in about like the 1920s approximately, where chlorofluorocarbons, what am I spelling? Holy smokes. Fluorocarbons, or abbreviated as CFCs, are introduced as a refrigerant. And when I say refrigerant, what I'm referring to is the way a fridge works is compresses a molecule, a chemical down. It will pump it through a little tiny nozzle, which causes it to expand into the gas phase. And in doing so, that's what's called an adiabatic expansion. I'm not going to quiz you on this, so don't worry. And that expansion actually causes the molecule to cool down significantly. And if you have that in like the lining of a fridge, you can put stuff inside of it and that stuff will get cold. So refrigerants historically, so before CFCs, one of the most common refrigerants was ammonia or NH3. And if you know anything about ammonia and the history of like Fritz Haber and the Haber-Bosch process, you'll know that ammonia is used in some cases to make explosives, to make weapons. So it's not a real good thing to have a refrigerant that doubles as an explosive. That's a pretty bad thing to have just sitting around in your kitchen, So the discovery of chlorofluorocarbons were really monumental because what was nice about them, so CFCs are incredibly inert. They don't really react with anything. And so when I say inert, I mean don't react. So we don't have to use an explosive anymore for a refrigerant. We can use a chlorofluorocarbon. And I should mention that chlorofluorocarbons, like I mean, there's many different kinds, but it's basically a carbon atom bonded to something like 2 chlorines, 1 fluorine, or it could be a carbon with, 3 chlorines, 1 fluorine, stuff like that. So it's these simple molecules that are composed of just 3 atoms in different proportions, so carbon, chlorine, fluorine, and they act as really nice refrigerants, and they're incredibly inert. So if you were to dispose of it, you don't have to worry about throwing an explosive away like you would with ammonia. But with chlorofluorocarbons, you throw them out, even if they're exposed to the environment. At the time, what people thought was, well, they don't react, so they'll just kind of sit around in the environment and not do anything. What's the problem? Well, it turned out it was a big problem, okay? So we're going to skip ahead here all the way to about 1974. I guess I don't need the about symbol there. It was 1974, where researchers Rowland and Molina, I believe at UC Irvine, proposed that CFCs deplete ozone in the stratosphere. Which would not be good, right? And what Rowland and Molina proposed was that if CFCs were to diffuse up into the stratosphere, so if CFCs got into stratosphere, I don't know what's going on with my pen here. They can absorb UVC light. So not so unreactive after all. Because I'm sure whatever company was developing chlorofluorocarbons as a refrigerant were testing them and towards their reactivity in terms of tropospheric reactive conditions, where there's not a lot of UVC light. So what Rowland and Molina did in the lab was they saw that, hey, look, if you take a CFC, so let's just pick one of these up here that I did, like CCl2 F2. Let's just pick that one as an example. What Rowland and Molina, I don't think they did these experiments. I think another researcher did, and they sort of drew the conclusions of, hey, this could be really bad for ozone. But anyway, in the lab, if you take a chlorofluorocarbon, you expose it to UVC light, what can happen is you can form chlorine atoms, so just neutral chlorine atoms, plus this other stuff, like so. And this chlorine on its own is really, really, really bad, because what it can do is this chlorine atom, if it's present in the regions of the stratosphere where there's a lot of ozone, it can react with ozone to form ClO, or like chlorine monoxide. I guess it wouldn't be monoxide, but chlorooxygen, we'll call it, and O2, the molecule. And in doing so, it converts O3 to O2 without O3 absorbing any UVB light. So it's sort of circumventing that process. This chlorine is reacting with the ozone and allowing UVB light to skirt through the stratosphere, no problem. which is really bad. And what's also really bad about this is that Rowland and Molina proposed that, well, you can actually regenerate these chlorine atoms. We don't need to get into the mechanisms of how, but just trust me that they showed that this can happen, that this chlorine oxygen species that forms can be regenerated back into the active chlorine atom, which can then deplete more ozone. So it's what we call a catalyst, where it is regenerated through chemical processes and can just keep reacting over and over and over again. I think the number, if I remember correctly, was, a single atom of chlorine could deplete, like thousands upon thousands of ozone molecules just because it gets regenerated constantly. So this is really, really not good stuff. And I'm running out of room here on this slides here. I'm going to erase some of this stuff and scooch some things up. So just give me a sec here. Okay, let's try that. So luckily, all of this is really bad. Chlorine we definitely don't want in the stratosphere, but luckily, even if these CFCs were to make it up into the stratosphere, which is something that scientists didn't actually think was possible, people didn't think that the CFCs could move above the troposphere into the stratosphere because they're too heavy. But it turns out there's some complicated fluid dynamics that can explain how CFCs, a heavy molecule, actually can get up into the stratosphere, but just trust me that they can get up there, which would be bad because all of this, ozone depletion chemistry can occur. But luckily, chlorine atoms have stable sinks, is what we call them in atmospheric chemistry. So just a place for them to go to deactivate them. So I'll say this, that deactivate them, or deactivate the Cl, okay? So we don't need to talk about the chemical reactions that occur here, but in the stratosphere, chlorine atoms can be converted into hydrogen chloride, HCl, which, to those of you who might have had chemistry courses before, you would think, well, hang on, I've worked with HCl in the lab and it's incredibly reactive and dangerous, which is definitely true. So on the surface of the Earth, if you have HCl, it's a very, very dangerous and reactive thing, but in the upper regions of the stratosphere, this is a gas, and just trust me that it is actually very, very stable in those upper regions of the stratosphere, okay? So in the gas phase, HCl, pretty stable, relatively speaking. And then the Cl can also be converted into what's called chloronitrate, or ClONO2. And both of these things, these molecules, HCl and ClONO2, deactivate the Cl, where it will eventually, even if CFCs got up to the stratosphere, absorbed UVC light, and started forming these chlorine atoms, eventually these chlorine atoms will accumulate as HCl and ClONO2 and ultimately not do a whole bunch of bad chemistry and not deplete a bunch of ozone. And at this point, you might be wondering, well, why go through all this detail? Why tell us that chlorine's bad, but actually it isn't, because it forms these stable sinks? That's because we're not quite there yet. If you remember the history of this, or if you know anything about it, you'll remember that it was specifically an ozone hole above the Antarctic. So there's a little bit more at play here that we still need to get into. And I promise we're almost there. So if you're feeling very bogged down with all these details, I promise we're almost there, and I'll give a nice summation at the end to just remember what steps are important in this process, okay? All right, so up to this point, what we have here is that CFCs were very prevalent in terms of being used as refrigerants and cooling agents, so things like fridges and ACs. As they are disposed of, the CFCs can make their way up into the stratosphere, where ultimately, on a normal given day, they'll just form these stable molecules, HCl and ClONO2, okay, or chloronitrate. So let's now talk about the ozone hole above Antarctica and how those conditions specifically led to a mass amount of ozone depletion. Okay, so the events causing the ozone hole, there's a lot of figures on this slide. Let's just go one by one here. So first important detail is that seasons are important here. So specifically, a lot of the events that lead up to the ozone hole forming occur in the Antarctic winter and the conversion from winter to spring in the Antarctic specifically, okay? So you might know that the Earth is on a tilt as it is orbiting the sun. So when I say Antarctic winter, that is the point where the South Pole or the Antarctic region of Earth is farthest away from the sun, and in this portion of Earth's orbit, there is no light making its way to Antarctica. So you might be familiar with this. There's certainly been some pieces of art, like 30 Days of Night, I feel like is one, describing the winter in the polar region. But basically at the poles, when it's winter in those regions, the sun just sets and stays set for like 30 days and then comes back afterwards, okay? It might be more than 30 days. I don't know that exactly. But basically, Antarctic winter, no light. And remember, if there's no light, then the photochemical reactions that lead to the temperature inversion of the stratosphere do not happen. So if there's no light, can't find my mouse here. If there's no light, there is no ozone formation, no heat formation in the stratosphere, so the temperature as a result drops precipitously, very, very, very low. So Antarctic winter, no light, then temperature plummets. I'll just draw a downward arrow. It just spikes down, gets super, super, super cold. And because of this cold temperature, so the low temperature causes what are called polar stratospheric clouds to form. So rather than write out polar stratospheric clouds every single time, I'll just abbreviate them as PSCs. So down here, PSCs. So there's these little, really kind of beautiful looking clouds that appear in the stratosphere specifically. So normally clouds are residing in the troposphere. So that 12-kilometer cutoff of where the stratosphere starts, that is really the upper limit of where clouds can form. So in the winter, in the Antarctic winter specifically, the temperature is just so darn cold that the water vapor in the stratosphere starts to crystallize and form clouds. That's what clouds are, right? Suspended little water particles, okay? So if we were to zoom in on like an individual particle of water in a polar stratospheric cloud, it would look something like this. We would have a solid crystal of ice, and an interesting fact that actually stumped physicists for a very long time is that at any temperature, ice will have a thin liquid layer over it. So we don't need to go into why that is, and quite frankly, I don't remember my grad school classes well enough. I'd have to look at my notes, but anyway, there's a liquid water layer surrounding these ice particles, okay? So on this polar stratospheric clouds, there's all these little particulates with liquid water available. That's what's important here, okay? And what happens in this liquid water layer is the normally stable forms of chlorine, so HCl and ClO, these can actually diffuse into the water layer, and they can participate in reactions in the liquid phase. So, going back to HCl, those of you who have taken chemistry lab before will know that this is a very toxic and hazardous chemical. It is very reactive. And the reason you are taught that is because in the liquid phase, that is true. In the gas phase, it is much more stable, much less reactive. So now that this HCl can dissolve into water, into a liquid phase, it will become significantly more reactive and start doing stuff. And basically what happens is that the HCl, the hydrogen chloride, and I'm trying to figure out what color I want here. We can just do black. So both of these molecules, we don't need to get into the specific chemistry that's occurring here just because it's not that important. I might make my atmospheric chemistry students know this stuff, but for you it's not that big of a deal. What's important is the end result. So through a series of reactions, what happens is these are converted to Cl2, so molecular chlorine, okay? So just like the stuff that you add to water to disinfect it, or to swimming pools like bleach and stuff, it's all related to this. But anyway, so what happens here is these diffuse into the liquid layer on these polar stratospheric clouds, these ice particles, and Cl2 starts to accumulate into these particles. So these are just super duper full of Cl2. Okay, and then what happens next is as winter goes to spring, so I'll just say as light returns. So when Antarctic winter transitions into Antarctic spring, light returns, those photochemical reactions that produce ozone and generate heat start picking up again, and eventually, the stratosphere heats up. The stratosphere heats up, and the PSCs dissipate, or they go away, because it's too hot for them to remain. Those solid ice particles making up the clouds break apart back into water vapor, okay? And what happens now, that's really bad, I'll put it in red because that's really bad, Cl2 is liberated. Now I should mention that it's a lot of CO2 is liberated, because throughout all of the Antarctic winter, this Cl2 is just slowly accumulating in these polar stratospheric clouds, and as soon as sunlight returns and it's warm enough, these clouds dissipate, and there's just an abundance of Cl2 in the gas phase in these regions of the stratosphere, okay? And then what Cl2 can do, Cl2 can absorb UV light. I think it absorbs UVA, if I remember correctly, which I think I do. And it can form two chlorine atoms. Uh-oh, those same atoms that cause this catalytic ozone depletion are now just absolutely introduced in a really, really fast rate into the stratosphere. And what these do is these just absolutely destroy all of the ozone present. So these will just completely deplete the ozone. And remember, the reaction was Cl reacts with O3 to form ClO plus O2. And then this ClO can be regenerated back into active Cl, okay? And this, as a result, causes the Antarctic region specifically to have a massive ozone hole above it where there is just no ozone or relatively little ozone. And as a result, a bunch of UVB light is able to make its way to Earth's surface. And it can cause a lot of health effects in humans and other biological life. And it's just all around really, really harmful. Okay? All right, so just because that was a lot of information, let's just go through step by step what happens to form the ozone hole. So step one, Antarctic winter. That's a big one. So Antarctic winter, which means there is no light, and as a result, no heat. Well, I should say no heat producing chemical reactions, and this leads to the temperature dropping significantly. Okay, so step two, because of low temp, polar stratospheric clouds start to form. Normally, the stratosphere is too warm for water crystals and particles to form clouds. In the Antarctic winter, temperature is so low that polar stratospheric clouds can actually form. Okay, and then step three, HCl, messed up my C there, HCl and chloronitrate, ClONO2, dissolve into liquid layer on a PSC particle, so just like a little ice particle in the cloud, and are converted to chlorine, Cl2, molecular chlorine. I realize I do that a lot. I should probably be more careful about that, where I say oxygen, and that could mean the atom or the molecule. So I'll try to be better about that. Are converted to molecular Cl2. And then step four, as winter ends, so this would be like, I guess, October-ish in the Antarctic winter to spring transition, because remember, Southern Hemisphere, they have opposite seasons. So as winter ends, light returns, and PSCs dissipate. And then last step, Cl2 is liberated from the PSCs. Maybe I should just say released. Liberated makes it sound like it was held captive or something. I'm not trying to personify molecules here. Is released from PSCs and absorbs UVA light. So Cl2 plus UV goes to 2 chlorine atoms. And then last step, step 6, Cl atoms rapidly deplete ozone in vicinity, creating this just massive region around the Antarctic specifically where there is little to no ozone, okay? And it's important to note that this does not happen in mid-latitude regions, so think like around the equator. So around the equator, there's always going to be light, even in the winter. So there's going to be no polar stratospheric clouds that form. And as a result, steps, 3 is not going to happen because step 3 needs a particle for the HCl and ClONO2 to dissolve into for this liquid phase chemistry to happen, okay? And maybe that's giving you a nice preview to how wildfires can deplete ozone. So just remember, for all of this to happen, there needs to be clouds or some particulate matter present in the stratosphere for this liquid phase chemistry of forming Cl2 to occur, okay? But this is in general what happens in the formation of the ozone hole around the Antarctic, okay? And I guess just so this ends on a more positive note, all of these events led to 1987, the Montreal Protocol was signed. So this was an agreement between like all of the, or it's an international treaty between all of the nations in the United Nations and then like some other nations as well to ban CFC use and production. So now what is used is what's called hydrofluorocarbons, or HFCs, which are still bad for other reasons, but they don't deplete ozone, so that makes them marginally better. Well, not marginally, not depleting ozone is a very big deal. So hydrofluorocarbons, so this would be like, instead of the chlorine, this would be like CH2F2. They have now hydrogens there instead of chlorine. And as a result, if these were to get up into the stratosphere, which actually they can't because they're reactive enough that they react in the troposphere, but even if they got up to the stratosphere, they would not form chlorine atoms by absorbing UVC light, okay? So this was sort of the culmination, the end result of all of this science showing that this stuff happens was, several nations agreeing to no longer use CFCs and banning their production, okay? And before we get to the discussion on how wildfires deplete ozone, or I guess no, we'll just jump right in. So I guess just to highlight, why did we go over all of this history? Well, step 3 is really important. So step 3, HCl and ClONO2 need to dissolve into a liquid layer is a very important step that leads to ozone depletion. And I should mention also that HCl and ClONO2 are pretty much everywhere in the stratosphere because CFCs don't just migrate to the Antarctic to react there. They're sort of spread out and dispersed everywhere, and historically, it was just in the Antarctic where CFCs would be able to result in ozone destruction because clouds formed in the Antarctic during the winter. And I guess an interesting detail is that in the Arctic winter, so on the North Pole, it actually doesn't get cold enough for polar stratospheric clouds to form, so ozone depletion there isn't as big of a deal, okay? So the reasons for that we don't need to get into, but I digress. So remember, step 3, really important. These particles need to be present for HCl and chloronitrate to dissolve into and to form Cl2, ultimately resulting in ozone depletion as that Cl2 is released into the stratosphere and absorbs UV light, okay? All right, so now that we have this sort of stage set, let's transition to wildfires. How do wildfires deplete ozone? So you might wonder, how does stuff in smoke get all the way up into the stratosphere? That seems unlikely to happen. And the way, the mechanism of mass transport into the stratosphere is through what is called pyrocumulonimbus clouds, something you might have heard of before, where basically what happens in a severe wildfire is that the temperature mixing from the hot wildfire and the cooler surrounding air creates these upward drafts that can actually propel the wildfire smoke up into very, very, very high altitudes. Okay, so I guess step one for wildfires depleting ozone is pyrocumulonimbus clouds, which I don't remember how they're abbreviated. I think it's this. Let me check real quick. All right, I was a little off there. I was close, to be fair, but they're sometimes abbreviated. This is what I was thinking of. They can abbreviate as many things, but pyro-CB, we'll call them. So pyro-CB introduces, we'll just say smoke, which we loosely defined in our very first lecture as to what it was chemically, into high altitudes. It can actually go all the way up into like mid-stratosphere level. So like, remember stratosphere was like 12 to 48 kilometers. It can go all the way up to, like 35 kilometers, like pretty high up there. And as we recall from our first lecture on particulate matter, is that organic carbon or OC as it was abbreviated, is a major component in wildfire smoke, is a major type of particulate matter that is present. The major type, or variant maybe is a better word, whatever, you get the idea hopefully, of particulate matter in smoke. Okay, so this organic carbon is basically like formic acids, or just a lot of the stuff, a lot of the organic carbon in wildfire is stuff with carbon and oxygen and hydrogen, we'll say. So we'll say HY or HX, carbon Y, oxygen Z. I'll get rid of the formic acid thing here because we don't need to know that. But basically, it's just some combination of carbons and oxygens and hydrogens. And what's interesting about this type of particulate matter, organic carbon, in the stratosphere, so in the stratosphere, OC is a liquid, interestingly enough. Remember, particulate matter can be suspended, solid, or liquid particles in the atmosphere. So in the stratosphere, at least recent evidence suggests that this particulate matter, these smoke particulates, are in the liquid phase. And what's even more alarming is that HCl and chloronitrate are significantly more soluble in liquid organic carbon than liquid H2O. So remember what they did in polar stratospheric clouds was the chloronitrate and the HCl dissolved into this liquid layer in polar stratospheric clouds. In smoke particulates, this organic carbon, this liquid droplets of organic carbon, HCl, I guess I shouldn't say chloronitrate, but HCl specifically is significantly more soluble in organic carbon than in water. So technically, the data that's out there shows that HCl is significantly more soluble in liquid organic carbon. And what this means is, if we were to have a smoke particulate that is composed of organic carbon, so I'll just draw like a little droplet here and label it OC, a lot more HCl can go into it, and as a result, it can fit a lot more HCl inside of it, and this HCl can be converted to even more Cl2. So more HCl can dissolve into OC particles, ultimately causing more Cl2 formation. Okay? And the reason this is bad is because wildfire smoke can do all of the same chemistry that a polar stratospheric cloud does. Basically, it's all of the same steps we wrote out on this slide, except with wildfires, we're not talking PSCs, we're talking organic carbon particulates or particles. And every other step is pretty much the same. Sure, there's no like transition from winter to spring, but as these smoke particulates start to dissipate as the wildfire dies down, the chlorine that is formed, the molecular chlorine, Cl2, that is formed inside of these organic carbon particulates can do the exact same photochemistry as the molecular chlorine that causes the ozone hole. And it will react and deplete ozone in the vicinity. And what's especially alarming about this is that the ozone hole that we talked about earlier was focused, isolated, concentrated around the Antarctic. But because wildfires can occur really wherever there's plant matter, this occurs in mid-latitude regions. So the ozone hole over the Antarctic did not really affect mid-latitude regions. So when I say mid-latitude, think like the United States or Europe, or like regions of mid-Saharan Saharan Africa or South America. Those regions were not largely affected. I think the biggest region affected from the Antarctic ozone hole was Australia. But with this finding of wildfires depleting ozone, this occurs wherever there's a wildfire. So in a region like California, for instance, where there's a lot of wildfires, it's probable, based off of these results, this research showing that wildfire smoke can deplete ozone, that now people in this vicinity in that vicinity are at risk of being exposed to more UVB light as a result of ozone being depleted from wildfire smoke, which is really, really, really alarming. Okay, and just to address the last figure or the last image I have on this slide here, you might be wondering, well, hang on. We banned CFCs in 1987. That was a long time ago. Doesn't feel like it, but it was. That was, like 30 some years ago. That was a really, really long time ago. How is there still chlorine in the atmosphere? Because if we ban CFCs, how then do we form things like HCl or ClONO2? I thought that CFCs were the source of these. So if we ban those, 30 years go by, shouldn't all the chlorine be gone? The answer is no, not by a long shot. And that's what this last image I have here is. So this is showing current and projected ozone hole recovery over the Antarctic, okay? So, this is based off of current data in 2017, still a pretty large hole of ozone in this ozone hole in this region. And even by the time we reach 2041, 2065, assuming ozone depleting chemicals are not reintroduced into the stratosphere, the ozone hole will still be slightly present, okay? And this is because CFCs last a really, really long time. So CFCs last, like, the estimate, I believe, is 50 to 300 years in the atmosphere. So remember, when I told you earlier that CFCs don't really react, yeah, they don't really react, except really with ozone, unfortunately. And they persist in the atmosphere for a super duper long amount of time. So even though we banned CFCs 30 some years ago, there is still a lot of the products that CFCs produce in the atmosphere. So when I say that, I mean HCl and chloronitrate. There is plenty of HCl and chloronitrate in the atmosphere. So all wildfires really do is provide a medium through which HCl and chloronitrate can be converted into chlorine and therefore deplete ozone. Okay? Um, yeah, I think that's all I wanted to say with that image there, was that CFCs last a really long time. There is still plenty of chlorine in the stratosphere, still causing an Antarctic ozone hole. It is slowly recovering, but slowly, just because it takes a while for the chlorine to leave the stratosphere completely. And as a result, the smoke from wildfires can still deplete ozone because there is still plenty of chlorine in the stratosphere to do this ozone depleting chemistry. Okay, and we'll talk a little bit more about sources of chlorine in a second. But first, I just wanted to show you data from one of the sources that I was using for this lecture. So this was ozone depletion that was measured over Australia specifically. So if you think back to like 2020, like, oh God, coronavirus, yeah, that's what everyone thinks of. But think back to the very beginning of 2020, and you might remember that Australia was basically on fire, like entirely. So much of Australia was on fire. So there was a lot of data that was collected from those wildfire incidents, and one of the findings from the data collected was this ozone depletion. And it's very, very, very small. So if we look here, what's plotted here is altitude and then ozone concentration. We don't really need to focus on the units here. Just know that uh, there is a rise in ozone as you go up into the stratosphere. There's that ozone layer where it's sort of that Goldilocks zone where oxygen atoms can react with oxygen molecules, O2, to form ozone and produce heat. And what this is showing is the ozone levels in 2005 through 2019. So the average is about here. And then in red is what was measured in 2020. So very, very, very small. It's about like a 1% decrease, which you might think, well, who cares about a 1% decrease? But you have to be, I guess I didn't give this fact earlier, but ozone makes up such a tiny, tiny, tiny fraction of our atmosphere that even this small decrease can lead to some deleterious, harmful effects down the road. And I guess before I get into that, and in part B here, what we have is the ozone concentration from 2020 that was measured after the Australian Black Summer event minus the average ozone from 2005 to 2019. And you can see a very clear, distinct dip where it goes down, which suggests that it was the event of these wildfires that causes this 1% decrease. And you might think 1%, who cares? But remember, in our warming climate, wildfires will only get more prevalent. And this 1% decrease, if there are more wildfires burning throughout the year over a larger land area, this 1% decrease can add up to 2% to 4% year on year and cause really, really harmful issues. Okay. So this is sort of very early on detection of this problem, but it is still a problem nonetheless, okay? And then one last thing I wanted to talk about was the sources of chlorine for depleting ozone. So the big one, obviously, CFCs, even residual chlorine that result from CFC use, even though we banned them, over 30 years ago. The CFCs still produce a lot of chlorine. And then two, remember from our very first lecture, I think I have this on one of these slides. So in our first lecture, we talked about particulate matter, and chlorine was a big one. So why is there so much chlorine particulate matter present in wildfire smoke? And the answer is you can't really, pin it to one specific thing, but one big thing is pesticides, where chlorine is commonly present, let's say, in pesticides that are used in agriculture. And typically pesticides are some combination of like carbon, hydrogen, oxygen, and chlorine. So a famous one that is now banned actually is the pesticide DDT. And so there are naturally, anytime like a chemical gets banned, there's always like some replacement that still does the job of the banned chemical, but is just slightly less bad. So think like chlorofluorocarbons. They were replaced with HFCs. They still do the job as a refrigerant and a coolant, but they don't deplete ozone. But they still are a greenhouse gas and can lead to harmful chemicals in the troposphere. But that's sort of just like okay, I guess, to a company trying to make profits off of this stuff. But the same is true for pesticides. So DDT, I actually don't remember the chemical formula for this, so let me look that up real quick, and we can compare and contrast here. DDT was C14H9Cl15, or excuse me, not 15. That would be a very interesting chemical structure. Cl5. But it was some combination of carbons, hydrogens, and chlorines. So modern pesticides sort of mirror or mimic that chemical functionality, but in a way that is slightly less bad to be exposed to. Okay, so if a wildfire were to burn over a region, over a land mass where pesticides are used, it will introduce a lot of chlorine into the atmosphere and be an additional source that can deplete ozone should a pyrocumulonimbus cloud be able to cause all of that mass transport of particulate matter and wildfire smoke up into the stratosphere. So I guess just to summarize everything, wildfire smoke can sort of simulate polar stratospheric clouds, where in some cases it's actually better, meaning more effective at depleting ozone, because HCl is actually able to dissolve more readily into the liquid phase of organic carbon, and in doing so can form more Cl2. Then as the smoke particulates dissipate, as the wildfire dies down, more Cl2 present will cause a lot of ozone depletion in that mid-latitude region. Okay, so I think that's pretty much everything I wanted to cover for today. So next time, what we're going to be focusing on in this course is atmospheric processes in the troposphere. So we'll talk about cloud formation. There was a lot of interesting details I did not touch on in this figure. So notice that there's rain involved. We're not going to talk about lightning, unfortunately, but how does a cloud form as a result of wildfire smoke? So we'll talk about that. And then we'll also talk about more ozone, but this time ozone in the troposphere, which is where ozone is bad. You don't want ozone in the troposphere, you do want it in the stratosphere. Wildfires do the opposite of what is good for biological life. Wildfires deplete the ozone in the stratosphere and increase the ozone in the troposphere. So we'll talk a little bit more about that as well. So hopefully you found this lecture interesting. Please let me know if you have any questions on the material that we covered, and if not, that's totally fine as well. And that's all I have, so I will see you in the next video.